Hello friends, welcome back to our channel. So today we'll see the one more application on branch and bound, that is knapsack problem. So 1 knapsack problem. So already we have seen what is this knapsack problem in our previous sessions, and once again I'll tell you what is a knapsack problem and how we can solve this knapsack problem by using branch and bound. So knapsack problem using BNB. So BNB stands for branch and bound. So branch and bound is an algorithmic approach which gives the optimal solution. So which is used to find the optimal solution among different solutions. And here also we are going to use or draw the state space tree, but we are not expanding each and every node. So we'll use some boundary values, and based upon that boundaries we are supposed to expand only those particular nodes. So the complete state space tree will be reduced with the help of the boundaries. Okay, and here we are using the least cost branch and bound. Least cost branch and bound. That means we'll find out the cost for each and every node, and we are supposed to expand the node which is having the least cost. And see here, in this knapsack problem we'll be having a different weights and different profits, and there will be one knapsack, and we are supposed to push the weights into the knapsack so that finally we should get the maximum profits. And here everything will be the maximizations, but here we are considering the least cost. So initially we'll consider the complete profits with a negative value, and finally we'll get the positive. Okay, see, knapsack will be having one knapsack, that means a bag structure, okay, with a capacity, a fixed capacity, and we'll be having some profits and weights and the corresponding profits, and we need to add these weights into this knapsack so that the corresponding values should be more profit. Okay, more profit. So we can say it as a fill knapsack which gives more profit. Okay, so here the boundary, so here what is this 1 knapsack? 1. So we are supposed to consider 0 as push, or consider the corresponding weight 1. 0 for consider and 1 for consider. It's not consider and consider. For example, if we are having the weights as x1, x2, x3 and x4, and the profits with the p1, p2, p3, p4, then simply we will represent the solution with 1, 0, 1, 1. So how it represents means we are considering x1, okay, we are considering x1 and x3 and x4. So we are pushing all these three weights into the knapsack so that we'll get the profit as p1 plus p3 plus p4. That is a more profit. So if 1 represents considering the particular weight, 0 represents not considering the particular weight. So here 1, 0, 1, 1 means x1 is considered, x2 is not considered, so we have not written here. So p2 is also not available here, and 1, that means x3 is available, x4 is available. So for that representation we are considering, we are using this 0, 1. 0 means not considered, 1 means considered. So we need to expand the state space tree for both the cases. Okay, now we'll see an example of this knapsack problem. We'll solve that by using branch and bound. Okay, that's also least cost branch and bound. See, this is an example we are supposed to solve this. So profits are 10, 15, 7, 8 and the weights are 2, 3, 1 and 5. And the capacity of knapsack is 5. So we need to consider only the weights which gives the total weight 5 and which gives the possibility of more profit. For example, here you can see we can push the 2 and 3 into a knapsack so that the total weight will be 5. So the corresponding weights you can see 10 plus 15, which is nothing but 25. Okay, and there is one more possibility, pushing the last item only 5 into the knapsack because the capacity is itself 5, right? What is the profit? 8. So we can fill the knapsack with a 5 weight. So that 5 can be filled with single, pushing only the fourth element into the knapsack or the first 2 elements into the knapsack. So here we are having 2 different solutions. Among these 2, what we have to consider? We have to consider the optimal. Optimal means with a high profit. So if you push the 4th element into the knapsack, the profit will be 8. And if you push 2 and 3 into the knapsack, the profit will be 25. So which is an optimal? So obviously this will be the optimal. So we have to find these optimal solution with the help of a state space tree. Okay, so in that we are supposed to find the least cost BNB. So initially we consider the profit as a negative values. So the negative values are minus 10, minus 15, minus 7, minus 8. Okay, now let us consider initial node which is a root node. So from that root we are supposed to find the 2 paths. One is whether we have to consider the first element and we should not consider the first element. So we will be getting 2 nodes. Okay, and here for each and every node we are supposed to find the 2 things. One is upper bound and the lower bound or cost. So U for upper bound, cost is for lower bound. U is for upper bound, cost is for lower bound. And see, upper bound means the profits without fractions. For example, see, consider second and third elements. So 3 plus 1 is equal to 4. So still the knapsack can hold 1 weight. Okay, so it is 4. The capacity of knapsack is 5. So still there is a vacancy of 1 weight. So we can consider this 1 from the next element. So not the complete element can be pushed into the knapsack here, right? So here there will be some sort of fractions. So upper bound means the profits without considering the fractions. So we have to consider the complete element or we can ignore it. But coming to the lower bound, that is a cost, which is a profits of corresponding weights considering the fractions. Okay, so we'll calculate both, but we will be depending on the upper bound. So which node will be having the least cost, that will be expanded more. Okay, now we'll calculate the U and C for both the nodes. First, coming to this one, see, if it is x is equal to 1, that means we have to consider the first element. So what is the first element here? So 2 is the first element. So we'll consider the profit. If you insert this 2 into the knapsack, what is the profit? It is a minus 10. So there will be still 3 possibilities. I mean, the capacity of knapsack is about 3. So move to the second element, 3. If you push 3, we will get the profit as a minus 15. So check whether the knapsack has been filled or not. So 2 plus 3. So obviously it is 5, which is the capacity of knapsack. So no other element will be pushed into the knapsack. So if you add this one, the profit will be minus 25. Okay, minus 25. The profit is minus 25. So here we are not considering any fractions. So upper bound will be minus 25. And coming to the lower bound. So this is the upper bound, this is the lower bound. We need to consider the fractions if necessary. But here 2 is the first element and 3 is the first element. So there is no place in the knapsack. So there will be no fractions. And obviously the lower bound will also be minus 25. Okay, coming to this one, this node. So here we should not consider the first element. So without considering the first element, let us go with the cost. That means a lower bound, okay, with fractions. So we should not consider first element. So push 3 into knapsack so that we'll get the profit as minus 15. Then there is again vacancy of 2. So push the next element, that is 1. Okay, so that we'll get a profit of minus 7. And see, again we are having one weight, okay, but the next element is a 5. The next element is a 5. So we need to take 5, okay, 1 from 5, 1/5. So that we have, how we can take it as minus 8 divided by 5 into 1. So we require only 1. Okay, we need to get the profit of 1/5. Okay, so minus 8. So what it will be? So this is nothing but a 5. So 3, 1 and 1 from 5. So minus 15 minus 7. So minus 22. And here, what is this one? So 5, 8. Okay. So minus 0.4. Sorry, not 0.4. So 1.6. Yes, 1.6. So total it will be minus 23.6. That is the cost. Minus 23.6. Okay, hope you understood why we are getting the fractions. So here in this case, we didn't get the fractions because the first two elements fills the knapsack equally. So 2 plus 3, total 5. So there is no fraction. But here, coming to here, we should not consider the first element. We are not considering the first element. We should consider from the second element. So 3 plus 1, 4. And still there is a 1 element remaining, right? So we need to take 1 element from this 5 profit. So that's why we are getting here. And coming to the upper bound, we should not consider the profit. So we have to insert 3 so that we'll get a profit of 15. And we'll insert 1, we'll get a profit of minus 7. And there is no other element to be pushed because here we are having 5. If you push 5, total it will be getting a 9, which is beyond the capacity. So we should stop here. And the upper boundary is minus 22. So here we should not consider the fractions. So it will be minus 22. So among these, which is the least? Now you can observe why we are considering the negative. So here these are the profits, maximization profits. We need to get a maximum profit. So that's why initially we are considering that as a negative. So you can observe among these two, so upper bounds, consider the upper bounds. What is the least cost? So minus 22 or minus 25? Obviously, it is a negative. So minus 25 will be the least number when compared to the minus 22. So this is the minus 25 is the least one. So we need to expand this node. That means final solution will be including the first element. So we need to expand this one. So I'll expand here. So third and fourth. This is the second stage. Here we need to consider x2 is equal to 1 and x2 is equal to 0. That means we need to find whether we have to consider the second element, not to consider the second element. So repeat the same process. We have to repeat the same process. So here we have to find the upper bound. Here we need to find the lower bound. Here we need to find the upper bound, lower bound. For example, so in the previous case we have considered the first element, right? So here also we need to consider the first element. So first element is fixed. So inserting 2 will return a profit of 10 plus, if you consider the second element 3, which will give the profit of 15. And see the total capacity of knapsack filled, right? So we have to stop here and the profit is minus 25. But for both the upper bound and lower bound, it will be the minus 25 itself. And now we need to go with the second case where we should not consider the second element. So here we are not considering the second element. So you can observe we are considering the first element, we are not considering the second element. So we are considering the first element 2, insertion of 2 gives the profit of minus 10, plus we should not consider the second element. So this node is not considering the second element. So we need to consider third element, 2 plus 1, which gives the profit of minus 7. So is there any vacancy in the knapsack? Yes, the total weight of knapsack is 3. So there is a 2 more vacancy. So we need to take 2 from 5. So 2, 5. That means what we will get? Minus 8 divided by 5 into 2. Okay, so this will be minus 17 and plus how much we will get? So previously we got some 1.6, right? So 3.2. So which will be minus, okay. So which will be minus 20.2. Okay, so 8 by 5, which is 1.6 into 2. So that will be 3.2. Okay, 3.2 and 3.2 plus 17, 20.2, negative 20.2. So it will be minus 20.2. And here upper bound we should not consider the fractions. So we should not consider this one, right? So what is the cost here? Minus 17. Minus 17. Again, consider among these two nodes. So we should not consider this node. Okay. So among these two nodes, what is the minimum cost? What is the minimum cost? So here among this one, you can observe u is equal to minus 25, u is equal to minus 17. So minus 25 is the least cost. We need to expand 3 again. So in the third case, so we will give 5 and we will give 6 here. And we need to consider x3, or we should not consider x3. We should consider x3 or we should not consider x3. Both we have to find out. So we need to find the upper bound. We need to find the cost. Here also upper bound, cost. So here you can see x1 is equal to 1. So see, consider x1 is equal to 1, x2 is equal to 1, x3 is equal to 1. So if you consider x1 and x2, that means the first two elements if you consider, so 2 plus 3. And here the third case is we need to consider the third element also. If you consider the third element, the total cost will be 6, which is beyond the capacity. So we should not consider this. So we need not calculate that one, right? Because we should not consider. So here itself we got the total capacity, the knapsack has been filled. Coming to here, x3, if you are not considering the 3, see, considering 1, 1, 0. So 1, 1, 0, that means x1, x2, x3, 1, 1, 0. This is the case we are finding, right? So x1 is considered, so 2, we'll get a profit of minus 10, plus x2 is considered, we'll get a profit of minus 15. And x3 is not considered, so x4 should be considered. So if you consider x4, the knapsack capacity will be beyond. So we need not fill this one also. Okay, right? So the value will be minus 25 itself. So here it will be minus 25 and here also it will be minus 25. And among these two, which one is the lowest? Obviously minus 25 will be the lowest. So again, expand. So here there is another case, x4. So whether we need to consider x4 or whether we should not consider x4. So here also we have to find the upper bound and cost. Upper bound and cost. So you can see here at this position, what is this one? x4, it is 1. So we are considering 1 and 2 and 4. So 1 is 2, 3, and we are not considering this one, and the fourth one is 5. So if you add this one, what is the knapsack weight? So it becomes around 10, but the capacity of knapsacks is only 5. So we should not consider, and the weight will be minus 25 itself. And here also, if you are not considering the x4 also, okay, we should not add this one, right? So this cannot be expanded. We need not expand this one. Okay, and coming to this one, that means x4 is equal to 0. So we should not consider this one. So we are not considering this one. the knapsack weight is full. So with a profit of minus 25, so upper bound will be minus 25 and the lower bound will be minus 25. So that is the last step. So this is the solution for the problem. So pushing or considering the elements first and second will give the maximum profit. So previously we have seen the two cases, 2, 3. Inserting 2, 3 will be giving minus 25 as a profit, and inserting only the 5, single 5 will give the profit of minus 8. So you can simply remove this minus. Okay, you can simply remove this minus, so we will get the optimal solution. The highest profit is 25. So you can see by considering 2 and 3 we will get the more profit. And here also the same thing, we have expanded. See, we have expanded, we are considering, so we have not considered the second one, fourth one, fifth one and seventh one. So we have considered the node 1, 3, 6, 8. So node 1 by considering x1 first element, node 3 by considering the second element, node 6 considering 0, not considering the third element, and node 8 not considering the fourth element. So 1, 1, 0, 0 will be the solution to get the maximum profit. And in this case we are not giving the complete state space tree, we are not drawing the complete space state tree. So we are limited to the boundary, that is we are considering the least cost value of upper bound, and we are expanding only that particular branch instead of expanding all the nodes, right? So that's why we are calling it as a branch and bound. So we need to divide that branches, that means we need to draw the state space tree by considering the boundaries. And what is the condition? Least cost. And here we need to get the maximum profit. So obviously we are supposed to take initially them as a negative values, and finally we can ignore the negative values, so that we'll get the optimal solution for this knapsack problem. Right? So hope you understood what is a knapsack problem, what is a 0 by 1 representation, what is a branch and bound, what is a state space tree, and what is the constraint we are using the state space tree to be expanded, the each node to be expanded. Right? So practice more problems so that you will be getting strong knowledge on this branch and bound. Okay, so let's stop here, and if you enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much.